please make sure that you have this PowerPoint presentation printed so that you can take notes as we go through the examples. So in the last PowerPoint on the law of sines, we looked at setting up a proportion between the side and the sine of an angle to find either the side or the angle of the triangle. What's going to happen this time around is that we have two sides and an angle, and we are going to have to determine what happens. This is known as the ambiguous case. We may have one triangle, we may have two triangles, or we have no triangles that form from the information that's given to us. And so we have to figure that out before we go tackle the problem so we know what we're looking for. So this ambiguous case happens only when we're looking at side-side angle. And you may remember that side-side angle was a bad scenario when you were trying to prove that two triangles were congruent. Angle, side, angle, 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 side, 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 side. Those were all legitimate trig or triangle proofs for congruence, but side-side angle was bad, and we're going to investigate closer as to what happens with side-side angle if you didn't get a chance to do that back in trig or back in geometry. So let's take a look at this particular case. We will be using the law of sines, but we have to investigate what kinds of triangles we have first. So in every one of these scenarios, the setup is going to be that we have angle A, side A, and little b. So it's AAB. And we'll be looking to find the other components. So we're trying to see how those pieces fit together to create a triangle. So there's three different scenarios that happen with the ambiguous case. In this option, angle A is greater than 90 degrees, so it's obvious right away. And the first thing that happens is that side A is too short to reach side C. So little a is less than or equal to little b. This is violating the triangle inequality theorem. But what happens is that a triangle doesn't form, so there is no possible triangle. If we have an obtuse angle and A is big enough, then we get exactly one triangle. So here's an example. We have the angle as 120 degrees, and then little a is 22 and little b is 15. So little a is bigger than little b, and that means a triangle is going to form, and we need to find the missing pieces in here. So I have little a and big A, so I'm going to set up that as my beginning fraction. And then I have little b, and I need to cross multiply. And divide by 22. But now to get b by itself, I need to use the sine inverse of the lovely fraction that I have up there. And that's when a calculator is going to come in very handy. So we find out that B is about 36.2 degrees. And then we already know angle A is 120 degrees, so angle C is 180 minus 120 minus 36.2. Which would be about 23.8 degrees. You could also find angle C by setting up a similar fraction and doing the inverse sign to get angle C. But I think this is much faster. Okay, and this is just to give us some more work to find little c, but I did it using subtracting from 180. Okay, so when angle A is acute, this is when we're going to have more problems. To find out if our side is long enough to reach we are going to have to check out if the height here is going to be able to be the right size to have a triangle form over here. And so there's several possibilities that can happen when comparing to this height. So if we need to find the altitude, we're going to call that h for height. This height, when compared to our angle, if we think about it here, that is our opposite. So I'm talking about a sine, and it's a right triangle, so there's a hypotenuse that we're working on. So let's see how we can figure out that height. So finding the sine of this angle, that is our opposite over hypotenuse. So if we want to find h all by itself, I'm using the ratio of up here. So to get h alone, I need to multiply each side by b, and I would have h equals b sine a. And that h is the height of the triangle. And I'm going to compare it to the two sides that are given to see if my little a is long enough to make triangles, or if I have other problems. So if little a is too small, then little a is not going to reach, and I have no triangle. It just kind of swings back and forth. If little a is in between the height and the length of b, I have two triangles, and I have to find all the measurements for both triangles. But as you can see over on this side, here's my acute angle, and I get this very nice triangle. And over here, same acute, same length, totally different value for B, totally different length for C. Last but not least, A is longer. It's the longest side, and so I only get one triangle. So that's three different possibilities when A is acute, I could have one triangle like I do here. When A is bigger than H, and when A is the longest, I could have two triangles when A is in between B and H. I could have no triangles when A is too short. So I need to consider this H value. I have to find that. And if we think back, H equaled B sine A. So I have got to find that and compare it to A and B. So let's take a look. If I know that angle A is 40 degrees, and I have a value of little a of 12 and a little b of 15. First thing I need to do is find the height as b sine A, which gives me, let's see, 15 sine 40, which equals 9.6. Okay, so little a is long enough. That's clearly going to make it all the way down here. And A is smaller than B, so we are going to have two different triangles. And we need to find the solutions for all of the two triangles. So I'm going to focus on finding everything for one triangle, and then I'm going to do all my work again to find the second triangle on the next slide. So in our first triangle here, we will solve just as if we would using the regular law of sines to find angle B, angle C, and little c. So and then once we find angle B, we can get angle C by subtracting from 180. Now, to find the second triangle, we still have that little a is 12, but the issue is over here with angle B. It's no longer going to be the same value as the original B that we solved for. But what happens is the sine of that B is going to be the same. And so the sine would be the same if it was different by 180 degrees, or if it was subtracted from pi. If you remember that from when we were solving our trig equations, that based on our sine graph, like this, we would get the same value over here that we would over here. and it's because right there, which is at pi, or 180, since we're now using degrees as opposed to radians when we were solving our trig equations, we will be subtracting from 180 to figure out the other value. And in order to keep these separate, like I call this B1 because that was in my first triangle, and I call this B2, I don't know if you can see that very well, I'll erase my circle, B2 because it's in my second triangle, so B2, we subtract off the 53.5 that we found, and this now obtuse angle is 126.5. So if I know that, let's see, this is B2, this is going to be C2, and what else do I need to find? Oh, little c2. I can go find little c2 pretty quickly. So 180 minus 40 minus 126.5. I find out that angle C2 is 13.5 degrees, and that's capital C2. And I forgot to do this on my first triangle. I didn't find the length of the side for little c, but we'll do that here. We'll take little a over the sine equals little c2 over the sine of big C, and go solve by cross multiplying. And we find out that little c2 needs to be about 33. So, whoops, apparently I made a mistake. Hang on, let me go back and calculate.